Hi everyone, it's Miss Morales and I want to welcome you to Advanced Placement Calculus. Now before we begin, I want to introduce you to the fathers of calculus. The first was an Englishman who was a famous mathematician, physicist, and astronomer, and his name was Sir Isaac Newton. And the second was a German mathematician by the name of Gottfried Leibniz. Now, even though they're both credited with being the fathers of calculus, they didn't invent calculus together. In fact, they were working on calculus independently at around the same time, and there was some controversy as to who actually discovered calculus first, but now, many years later, most mathematicians agree in the mathematical community that they should both be credited as the fathers of calculus. So what is calculus? Calculus is known as the branch of mathematics that studies rates of change. So the concept of rates is one that we should be familiar with, but we want to take a look at it from a couple different perspectives. So we want to look at what is a rate from an algebraic perspective. So when we think of an algebraic perspective, we want to think of it in terms of symbols and equations. So a pretty familiar equation involving rate that I hope you all remember is that distance equals rate times time. Now if I want to look at specifically rate, I want to divide both sides here by time so that I get that rate is distance divided by time. Well, we want to introduce a little bit more mathematical notation, so I'm going to write that as the change in distance over the change in time, using this Greek letter delta to represent the idea of change. So delta is a Greek letter and it means change. So a rate is really a change in distance over a change in time. Now I want to be careful with that because in fact this really represents only an average rate of change over a particular time interval. So let's talk about what that means by going over a quick example. So let's say the distance from here to Las Vegas is 180 miles, and you left at 9 in the morning driving down there. On average, how fast did you drive if you arrived at noon? So taking a look at this formula that we have, the change in distance over the change in time, our average rate is going to be 180 miles over the total time elapsed, so 3 hours from 9 a.m. to noon. So simplifying the 180 over 3, we are going to get that on average we traveled 60 miles in 1 hour. And we're used to seeing this on our speedometer as mph, but it's really a rate, 60 miles traveled in 1 hour on average. So I keep stressing on average here because when you went and turned on your car when it was sitting in your driveway, it definitely didn't automatically jump to 60 miles an hour. We had to start at 0 miles an hour, and then as we're driving at any particular time, we might be going 65 miles an hour, and then we had to step on the brakes and travel 55 miles per hour. So this average rate of 60 miles an hour is representative of what happened over the entire time interval, not at any particular instant. So this is really an average rate of change formula, the change in distance over the change in time. So now I want to take a look at rates from a numerical and a graphical aspect. It might not be very realistic to write down while you're driving different times and the current rates that you are going at that particular time. So you wouldn't write down at 2:54 p.m. I was traveling at 50 miles per hour. But something that we do keep track of in a numerical fashion or in a graph or a table might be our height. So maybe over the years your parents measured your height as you grew, and when you first were born, maybe your height was 20 inches. And then 1 year later you took your measurement of your height again and you were 24 inches. 5 years old, 4 years later, we recorded your height at 36 inches. And then finally, let's say recently, at 16 years old, you are a height of 64 inches or 5 feet 4 inches. So this is the type of information that we would put in a table so that we can take this information and put it into a graph. So graphs tend to tell us a lot, if we're more visual learners, about what is really happening over a particular time. So let's take a look at this graph. On what is normally the x-axis, I'm making it the t-axis, and each of these increments is in terms of years. And then along what would normally be my y-axis is my h-axis, because I'm going to let that stand for the number of inches that I grew every year. So here you'll notice these little diamonds represent my height as a function of the number of years I've been alive. So at time t equals 0, I was 20 inches. At t equals 1 year old, I was 24 inches, all the way to I'm 16 years old, so now I'm 64 inches. So we want to somehow tie this into this idea of a rate, which we said in the last slide that rate is the change in distance over the change in time. Well, I don't have a distance here per se, but I do have this change in height. So let's take a look more specifically at what's happened between the age of 5 and the age of 8. And I can look at the change in height that occurred is that I went from being 36 inches tall to 48 inches tall. So in other words, I grew 12 inches over the course of 3 years. So what I'm really looking at here is a rise over run, which should strike you, and you should be thinking of the idea of slope. So graphically, this idea of a rate is really what we would refer to as a slope, and we tend to use the variable m for slope. So I'm going to call this slope m1, and I'm going to go ahead and label it as the change in height over the change in time. So a change in what would normally be the vertical axis, the y-axis, over the change in what happened horizontally, in this case the t-axis. So we grew positive 12 inches over a time frame of 3 years. So we grew an average of 4 inches per year. We cannot leave out that average. We don't know specifically what we grew at any particular moment, but we know between 5 and 8 years old, we grew an average of 4 inches per year. We can go ahead and do the same thing, figure out the average of our rate of growth between the ages of 8 and 16. We'll go ahead and call that slope m2. And we can see that it's the change in height over the change in time, this time 16 inches, going from 48 to 64, over the difference between 6 and 18, so 8 years. So between the ages of 8 and 16, we grew an average rate of 2 inches per year. So here you'll notice that the average rate of change was a greater number between the ages of 5 and 8 than between the ages of 8 and 16. So we grew at a faster rate when we were younger, as opposed to when we grew older, it looks like our rate slowed down. And that's represented by the steepness of the slope. So the connection I want you to make here is that we've so far seen a symbolic representation of rate as distance over time, or change in distance over the change in time. We took a table of information, a numerical approach, and then put it on a graph to connect the slope to that concept of rate. So now the question is, why do we even need calculus? I understood rates of change right now. We didn't do any calculus so far, right? Well, we need calculus because we want to solve real-world problems. Now the difference is that without calculus, we could solve problems with constant conditions. We can find the average rate of change. However, we want to be able to solve problems where there's constantly changing variables. So more realistically, we don't drive on roads that are always perfectly flat at the same exact mile per hour rate. No, we go over hills and we go different miles per hour and we stop at different areas. So calculus really allows us to solve real-world applications. So what's the reputation about calculus being so hard? So far, what I've heard about it isn't too bad. Well, I don't really think it is that bad. As long as you remember that mathematics in general is known as the universal language. The language that we should all be pretty familiar with, the English language, we've been learning since we were really small, and it was consistent of a bunch of different parts. So the first thing we did was we learned the alphabet. Well, the alphabet in mathematics is like learning arithmetic, your basic addition, subtraction, multiplication, division. And then we learned phonetics of each of the letters in the English language. And then we learned the parts of speech and how to make sentences. Those all correlate to the different areas of mathematics. So you can kind of think as you're writing a full essay as your problem-solving skills and critical thinking in mathematics. So It's a matter of the building blocks. Do you know the building blocks to be able to move on to the more difficult concepts? Calculus is considered a little more difficult because it requires a mastery of all the mathematical topics you have ever learned. Now, just like learning a language, it's definitely a challenge if it's not the language that you first learned when you were growing up, but all it requires is practice, practice, practice. Now, you will get plenty of practice in this class so that you can become more than proficient in the subject of calculus. Here are some common pitfalls that I have found. Students who tend to think that calculus is all about being able to memorize and that there's no studying that we can really do in math tend to not do so well. Calculus is not just about mechanics and memorizing. Instead, the real idea of calculus is to help you learn the concepts. What is really happening beneath the question? What's happening in the background? How do I apply this to a real world situation? Because that's what calculus is all about. So I really want you to keep that in mind throughout the year, that if you think it's all about memorizing the formulas, you're not going to be as successful as those who understand walking in that it's about learning the concepts. The way we're going to learn the concepts is to follow the rule of 4, and this is really what the AP program and college boards stress, that when we solve or kind of tackle any problem, our goal is to be able to analyze and understand that problem using the rule of 4 different areas. So we want to analyze every problem algebraically or symbolically, just like we did with that rates problem. We want to understand it as an equation with different symbols. We want to understand it numerically with a table of data or a chart. We want to understand it graphically, so we plot those points on a graph so that we can get a visual of what's happening. And we're going to have to be able to do this with and without a graphing calculator this year. And the last one, and I don't mean to put it last because it's not as important, in fact it's very important, we want to understand problems so well that we can explain them verbally or in a written context. And we want to do that using mathematical language. So the idea is if you really understand a problem, you will be able to give a written explanation of what is happening with the correct mathematical notation. So, sticking to an algebraic approach, using symbols, using tables, and using graphs, and then being able to talk our way through it is going to end up being our goal this year. In particular, my goal as a teacher this year is to really make you think. My goal is not for you to just pass the AP Calculus test. The AP Calculus test is just a test. The real crux of AP Calculus is critical thinking skills, and that's what I want you to walk away with, because even though you may not be a math major or an engineer, every single person, no matter what your college major is going to be, needs those critical thinking skills. So my goal as a teacher is to get you to think. So there are a few branches of calculus that we're going to look into this year. So calculus is divided into two really big branches, the first one being differential calculus, and the second one being integral calculus. And those are the topics covered in AB this year. If you are one of the few members of the BC class this year, we're going to go a little bit further and talk about this concept of infinite series, which involves sort of both differential and integral calculus. So you should have come from, recently, a pre-calculus course, and then prior to that taken all of the previous classes. And the question is, how are we going to get from pre-calculus to calculus? Well, we're going to get there using the idea of limits. So that should have been the last topic that you covered in your pre-calculus course, and you should have seen some of that material in your summer work. And that's what we really need to make this jump from all these pre-calculus topics to this bigger concept and this bigger subject of calculus. So now with all that in mind, I'm going to ask you, are you ready to take AP Calculus? So I hope you're as excited as I am to dive into this subject that not very many people really in the world ever get to. So be proud of yourself and be excited that you're willing to take on this challenge. And I hope that you show up to class looking more like the guy on the left rather than looking like the guy on the right.